Okay, now we are looking at section 9.2, and this is the last one that we're going to cover in this class. So section 9.2 is on so-called regular Markov chains. And before we do that, I'd like to discuss something called stationary matrix. Now let me start off with an example, and I'm going to open up a sort of a calculator that I have here, and let's see if I can make the font a little bit bigger. It would have been good if I thought to do this earlier. Okay, bigger, bigger. Hold on. Bigger, 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 bigger. Okay. And let me make the window smaller. Okay. So I'm just going to take just a completely random transition matrix. Let's say 0.7, 0.3, 0.2, 0.8. This is a valid transition matrix because if you add across 0.7 and 0.3 add to 1, 0.2 and 0.8 add to 1. Let me just change this a little bit. Okay, so there's our matrix P. I'm also going to start off with just a random initial state matrix. S is going to be, let's say, 0.5, 0.5. Again, in initial state matrix, the entries have to add up to 1, which means that half of the people here, for example, are in state 1, half are in state 2. Okay, let's see what happens when I continually multiply the state matrix by the transition matrix P. So after one iteration, we end up with 0.45, 0.55, but let's see what happens when we keep multiplying. That's after 2 iterations, after 3, after 4, after 5, after 6, after 7, after 8, after 9, after 10, after 11. Look at what's going on. These matrices look like they're approaching 0.4 and 0.6. If I just keep going, basically it looks like I've gotten there. What happens when I multiply P? So let's call this big S 0.4, 0.6. So S times P, I just get that matrix back when I multiply S by P. So in fact, this is something that's called a stationary matrix. So what we've seen is, if we have P equal to 0.7, 0.3, 0.2, 0.8, and for S0 equal to, what was it? It was 0.5, 0.5. We saw that the SKs got closer and closer to a matrix, 0.4, 0.6, which we'll call S. And we just saw that S times P is equal to S. So we call S a stationary matrix because it is stationary under the multiplication by S. Okay, so let me give the explicit definition. So definition. So if P is the transition matrix for a Markov chain, a stationary matrix is a row matrix S, which has entries that are greater than or equal to 0 but less than or equal to 1, and the sum of the entries is equal to 1. I mean, that just means it's a state vector or state matrix, which have always satisfied these uh, things. But the most important thing is that S times P is equal to S. So this is the main condition. It is something that is not changed by multiplying it by this transition matrix. It says that if we start with this distribution S and then we go forward one period in time to see, how things change after the transition matrix, nothing changes, at least in terms of the distribution. Let's recall our Verizon example where I said that we had the transition matrix for people switching from Verizon to other carriers. 90% of Verizon customers stayed with Verizon, whereas 10% of them changed, and 5% of non-Verizon customers went to Verizon, whereas 95% of non-Verizon customers stayed with other carriers. Now I'm going to let S be the matrix 1/3, 2/3, and I claim that this is the stationary matrix here. So S times P, that's 1/3, 2/3 times 0 0.9, 0 0.1, 0 0.05, 0 0.95. Now this is equal to this row times this column, so that gives me 1/3 times 0.9 is, I don't mean to write it like that. Let me start writing this up here. Okay, so 1/3 times 0.9, that is 0 0.3. In fact, let me write that as 3/10. 1/3 times 0.9 is 3/10, plus 2/3 times 0.05 is going to be 1 over 30, it turns out. And the other guy is 1/3 times 0.1, so that's going to be 1/30th, plus 2/3 times 0.95. 2 times 95 is 190. I guess that's right. And 190 divided by 3. Yeah, 190 divided by this gives you 19/30ths. Sorry that I'm sort of poorly doing the arithmetic in my head. Anyways, what this works out to is this is the same thing as 9/30ths. So I end up with 10/30ths and 20/30ths, which is equal to 1/3 and 2/3. Great. Try this out yourself with a calculator if you're not entirely convinced, because I don't think I really communicate the arithmetic very effectively here. But I don't really have the time to go back and edit, so sorry about that, folks. Okay. Now, this sort of thing, there are various kinds of Markov chains, and the ones that we're going to be studying are called regular ones. But let me go back to an example from section 9.2. This is going to be something that we are not going to consider. In fact, let me just sort of draw a simplified version of something like this. Let's say we've got three states, A, B, and C, and let's say that I can get from A to B half the time, and from B to A half the time, and from A to itself 20% of the time, and from A to C 30% of the time, and from B to itself 10% of the time, and from B to C 40% of the time. Let's suppose that from C you can only get back to C. This would be something called an absorbing Markov chain, because there is one state C absorbs, by which I mean it basically everybody, once you get to C, you never leave it. And when you have this sort of thing, it turns out that there are going to be generally infinitely many stationary vectors. well, maybe not in this case. In this case, I think there might only be one, but generally there might be, it's a little bit weird. But what we're really interested in this section are Markov chains where you can eventually get from any state to any other. So that's what a regular Markov chain is going to be. But here's the formal definition. So a Markov chain or its transition matrix P is regular, so the chain itself or the transition matrix is regular if some power of P has only positive entries. In other words, no zero entries. Because all the entries are bigger than or equal to 0, so we're just saying that some power of P has no zero entries. Well, let's note something. If a matrix, if a transition matrix has positive entries, what that means is you can get from any state to any other. The probability of you going from one state to another is non-zero. So in fact, the intuition for what regularity means is even though after one iteration of the transition matrix, after a certain number of periods, you can get from any state to any other state. So you never get stuck anywhere, you never get stuck in a couple of states. You can jump around between any collection of the states. So let's quickly look at just some sort of abstract examples of regularity. So for example, if we look at our Verizon matrix, if P is 0.9, 0.1, 0.05, and 0.95, well, this is clearly regular because it already has all of its entries bigger than or equal to 0, or bigger than 0. How about something else? Let's look at the matrix P equal to 0, 1, 1, 0. Well, let's start looking at the powers of P. P squared, 0, 1, 1, 0, 0, 1, 1, 0. When I multiply this row times this column gives me 0 plus 1. This row the first row times the second column gives me 0 plus 0. The second row times the first column gives me 0 plus 0. And the second column plus the second row times the second column gives me 1 plus 0, so it's 1. This is the identity matrix of order 2. So what is P cubed? Well, it's the same thing as P squared times P, which is the identity matrix times P, and the identity matrix is like 1, so it's P. So this actually shows that that P to the K is equal to P when K is odd, and the identity matrix when K is even. And neither of these has entries that are all greater than 0. Each has entries that are equal to 0. So this is not regular. So after a certain number of states, I either stay still or I go to the other guy, but I can't, there's no, fixed number where I could possibly be in one or the other. Okay, let's look at a third example, and for this example, I'm going to go back to my little calculator, and let's consider the following matrix. The first row is all 1/3. The second row is 1/2, 1/2, 0, and the third row is 1, 0, 0. Now let's call this P. Okay. So this does not necessarily look like it's going to be regular. I can't tell because when I look at it, well, I see a 0 here and 2 zeros here. But what happens when I take P and square it? Okay, when I square P, everybody suddenly has non-zero entries. All of these are positive entries. So this says that this guy is actually regular because after two iterations of the matrix, I can get from the first, second, or third state to the first, second, or third state. Okay, great. So 1/3, 1/3, 1/3, 1/2, 1/2, 0, 1, 0, 0. This is regular if P is that. If this is P, then this is regular since P squared has all entries greater than 0. Let's look at a similar looking one. This time, though, instead of having it's basically the same matrix, except I'm putting 1, 0, 0 on top, 1/2, 1/2, 0 next, and 1/3, 1/3, 1/3 on the bottom. So let's see what happens there. Again, going back to my little calculator. So 1, 0, 0, 1/2, 1/2, 0, 1/3, 1/3, 1/3. Now this is my new P. Well, what's P squared? 1, 0, 0 is still the top. What's P cubed? 1, 0, 0 is still the top. There's still a 0 in the second row. P to the fourth, 1, 0, 0 is still the top. You could generally show that for any power of P. Whoa, that's crazy. This is P to the some crazy power. For any power of P, the very first row will always be 1, 0, 0. The second row will always have a 0 here. In fact, these other numbers are so small that if I'm going to round this matrix, it essentially looks like 1, 0, 0. Okay. Cool. Great. So this is not regular since, for example, the first row will always stay the same. So that is not regular. That is not the sort of thing that we want to consider. And